to call upon Mr. Muhammad Faris Shafiq Khalid to present his paper entitled Effect of Nanosilica Modified Epoxy on Tensile Properties of Arenga Pinnata Polymer Composite. He's from Universiti Teknologi in Malaysia, and you have about 15 minutes, I think, because we have enough time. And then after that, maybe about 10-minute Q&A. Okay, please welcome Mr. Muhammad Faris.
All right, thank you, Prof. Sapuan. Okay, I'm trying to share my screen right now. Okay. I'm sorry, can you see my screen?
Yes.
All right, right. Thank you so much. Okay, Assalamualaikum and good day. All right. My name is Muhammad Faris Shafiq Khalid. Okay, actually, I learned on Arenga Pinnata or sugar farm also from UPM, Prof. My mentor at first is Abdul Hakim, Dr. Abdul Hakim.
He was my student also.
Yeah, right now he's a lecturer at UITM. And then in my master, my co-supervisor is Dr. Jawahir. All right, so I will start my presentation. Okay, so with me is Prof. Associate Professor Dr. Aida Johor. She's my co-supervisor, and also my colleague Muhammad Fazli Ismail. So my title is on effect of Nanosilica modified epoxy on tensile properties of Arenga Pinnata polymer composite. Okay, so this is a little bit on my presentation outline. So we will take a look on the introduction, a little bit introduction on the advantage of natural fiber and so on, and then a little bit on methodology, result and discussion, conclusion and acknowledgement, right? And then I will start my presentation with the advantage of natural fiber. Natural fiber have attracted the attention of researchers and manufacturers since years ago due to the advantage of having abundance of resources all around the world, which allow them to be acquired at low cost. It is also environmentally safe due to their biodegradable nature. Other than that, it's also less harm to human body compared to synthetic fibers such as glass fibers. Besides, natural fiber have a good mechanical properties and low density. Okay, and on the Arenga Pinnata is a tree also known as a nau or kabung in Malaysia, and been popularized by the name of sugar palm. Okay, sugar palm by UPM. At first, I learned on sugar palm, and then it have several names. Okay, it is also known as ijo or aren, injo anua, and 150 other different names in Indonesia. It is a fast-growing plant which only need around 10 years to reach maturity. For the geographical distribution, Arenga Pinnata tree can be found from Southeast Asia to Southeast Asia, and Taiwan to the Philippines, Indonesia, Papua New Guinea, India, Thailand, Myanmar, and also in Malaysia. Some usage from part of Arenga Pinnata tree are the first from the palm sap. We can obtain palm nira or fresh juice, and this can be used to produce sugar block or crystal and brown sugar. Okay, from its trunk we can get a starch to be used as a biopolymer. From its fibers around its trunk, we can get seawater resistant fiber. This is what we call a sugar palm fiber or Arenga Pinnata fiber. It can be used as a rope, broom, roof, substitute for geotextile fiberglass reinforcement, underwater and underground cable. And then from its fruit, we can use as a dessert. Actually, in Malaysia, we call it as buah kabung. Usually, we put it in a dessert called lychee kang. Okay, and lastly, from its leaf, we can use it as cattle feed. Okay, this is the tree, the Arenga Pinnata tree. As you can see in the slide, Arenga Pinnata tree on the left, and then it is produced black color fibers, okay, all around its trunk as shown in the zoom photo. The fiber had been harvested, prepared, and used in this research. Okay, so advantages of Arenga Pinnata, mostly known as for its resistance to seawater. Okay, as I've been mentioned in the keynote speech by Prof. Sapuan. It is also easy to extract the fiber from its source, and it is a high durability. Okay, for example of application as of now, Arenga Pinnata fiber already been used as a rope for thousands of years before, and fiber also been used as roof and broom. Okay, so problem that might be solved using Arenga Pinnata fiber polymer composites, such as replacement for construction of wood bridge at saltwater area because of its good properties. Okay, currently bridge and pathway that made from wood need to be maintained frequently. We need to do the coating for the wood around 6 months to 1 year once, and replace the plank every 8 to 10 years. Okay, and then this is on the nano composite, can be classified according to shape and dimension of nanofillers. There are 3 types. The first one is one-dimension nanofillers. It is a form of plates, I mean lamina or shell, which has plate thickness of less than 100 nanometers, such as clay nanoplate. And then for two-dimensional nanofiller, we include as a nanotube and nanofibers, has diameter lower than 0.1 micrometers or 100 nanometers, less than 100 nanometers, such as carbon nanotube, carbon nanofiber, and titanium oxide nanofiber. Right, and then what I will be using is Nanosilica. It is the three-dimensional nanofiller, consists of less than 100 nanometers dimension of three-dimensional nanoparticles, such as nanometric silica beads, okay, that have been used in this study. All right. So for the objective, the first one is the study to study the effect of Arenga Pinnata fiber content in Arenga Pinnata fiber reinforced epoxy composite, which we call it as APREC, and also to evaluate the effect of nanosilica content on tensile stress strain response and properties of Arenga Pinnata fiber reinforced epoxy composite. Okay, as you can see from this slide, Arenga Pinnata fiber were harvested from Kuala Pilah for this project, Negeri Sembilan, Malaysia. The raw harvested fiber, which has not been cleaned yet and contain Arenga Pinnata stick and also dirt, shown in the figure B, in the picture B. The cleaning process was started by removing the Arenga Pinnata stick and large dirt from the harvested fiber until remain with small dirt that is hardly to be removed by hand. Okay, the fiber then were cleaned using tap water to remove remaining dirt and dust. Lastly, the clean fiber will dry under sunlight for about 3 to 4 hours before placed in an open space under roof until it completely dry. Okay, it is easier to use Arenga Pinnata compared to Knaf, as mentioned also in the keynote speech before this. And then for nanosilica, we are using Nanopox F400. The name is Nanopox F400. We use in this study as a modifier for the epoxy. It was supplied by Evonik Industry from German in form of collodiazole 40% in epoxy resin. The size is average about 20 nanometers, and the largest one we found is around 50 nanometers. As for the production of nanosilica modified epoxy, the Nanopox F400 and epoxy resin was weighted as calculated to get a 5%, 13%, and 25 weight percent of nanosilica. Then the Nanopox F400 and Miracas 1517 was poured in glass beakers, and then we use magnetic stirrer at 400 RPM and 80 degrees Celsius. Okay, the mixture then was stirred for around 1 hour. After 1 hour of stirring process, the beaker containing nano-modified epoxy was placed inside a vacuum at pressure around 0.07 megapascal to remove the air bubble for duration of 1 hour. Okay, this is an important step for the stirring process because the problem with nanosilica is easy to agglomerate, okay, inside the epoxy. That's why we use this step. Had been proven by my supervisor, Associate Professor Dr. Aida. Okay, and then we move on the preparation of the APREC or Arenga Pinnata reinforced epoxy composite. So for the preparation of nanosilica modified APREC, the steps are the same with the preparation of unidirectional APREC. Okay, the step is the same. And then first, Arenga Pinnata in epoxy resin was weighted according to the volume percentage required. Then Arenga Pinnata fiber will align in the mold, in our rectangular shape mold in unidirection. The mold size is 250 millimeters by length, 25 millimeters by width, and 3 millimeters thickness. Okay, we use this mold size because we want to avoid the push from the unidirectional Arenga Pinnata. We want to get only a single angle from the arrangement. Okay, after that the Miracas, the epoxy was poured in the mold containing Arenga Pinnata fiber, and then we put a metal plate and put it in a cold press machine and press around 24 hours for curing process. Okay, after 24 hours, the specimen was removed from the mold and fill the edge of this, define the edge of the specimen for better finishing. Okay, so this is the specimen produced for this study. I have around eight type of specimen for this study. We have a pure epoxy, nano-modified epoxy, and also unidirectional APREC and nano-modified unidirectional APREC. Okay, and then okay, on the tensile test, we are using Instron 3382 universal testing machine with gauge length of 150 millimeters, following the ASTM D3039. Okay, the crosshead speed is around 2 millimeter per minute. Okay, so this is the result. Okay, before we go to the result on the nano modified, first we need to take a look on the Arenga Pinnata, or we call it as APREC first. Okay, we recap a little bit how and why we use 25 volume percent of APREC to produce the nanosilica modified one. Okay, this is the reason. Okay, actually this result was already presented in Botanica Journal, okay, from UPN, Botanica Journal of Science and Technology, volume 25. This is my research in 2017. Okay, from result shown in the slide, 25 volume percentage APREC give the best tensile properties, which increase 180.28% of tensile modulus and increase 27.63% tensile strength, okay, compared to pure epoxy specimen. So that's why we are using 25 volume percent for further on our nanosilica modified APREC. All right. So after we place the APREC, okay, we get the result. So this slide showing typical tensile stress strain curve for pure
I
epoxy.
interrupt, Dr. Khalid. Can you wrap up like in 2 or 3 minutes, please?
All right, okay, I will go a bit faster, okay. So the first result showing, okay, on the first graph, you can see the increment of stress strain of the curve starting from pure epoxy, and then when we add 5% weight percent, nanosilica also increase, and 13 and 25 accordingly, okay, the increment. And then, but for the graph B, you can see the increment only occurred from pure epoxy to 5 weight percent nanosilica APREC only. After we further use for 13, we embedded 13 weight percent nanosilica and 25 weight percent nanosilica. The composite, the tensile properties of the specimen reduced. Okay. All right. And then for the modulus also showing the same, as you can see. For the specimen without Arenga Pinnata, you can see the improvement on the resin, on the epoxy itself. Okay, the increase from pure epoxy to 5, and then increase on 13 and also 25. But when we use with APREC, only increase up to 5% nanosilica content only in APREC. Okay, why this is occurred? It is because we can see in the scanning electron microscope later on. Okay, but before that, I want to show you a little bit on the tensile strength. Okay, also the tensile strength also give the same result as the modulus, as you can see, only up until 5%. Okay, 5%. You can see the increment of the tensile strength, and then after we include up to 13 and 25, the strength become reduced. All right. So actually, this is occurred because of the improper weighting, which means that will be okay shown in here. We can see the electron microscopy image for specimen 5 nanosilica APREC at the top, and then for 25 nanosilica APREC, okay, at the bottom here at B. And then from the previous slide, we can see the addition of 13 and 25 reduce the properties. This reduction in tensile properties occurred due to high reinforcement content, high content of Arenga Pinnata and also nanosilica inside the composite. Okay, after we add 13% of nanosilica and 25% nanosilica. Okay, and then this had caused epoxy resin cannot perfectly coat the Arenga Pinnata fiber. This phenomenon, we call it as improper wetting. All right. As we can see in the SEM image over here, the matrix cracking occurred more severe from specimen 25 nanosilica compared to 5 at the top one. All right. Improper wetting also was caused by nanosilica mixed with epoxy resin had caused the mixture to increase its viscosity compared to pure epoxy resin.
How's the
Therefore,
timing
when,
now, Dr. Bidani?
Mhm.
How many minutes you have?
Yes, I mean, if you can wrap up like in 1 minute, that would be great because we're running out of
okay,
time.
okay, good.
We're going
All right,
beyond
okay.
schedule.
So actually, I want to show you that the addition further than 5 nano weight percent for this project will reduce the properties. Okay. As for the conclusion, I can say that if you want to add more nanosilica or nano content inside this Arenga Pinnata epoxy composite, maybe we will try a different method, maybe using vacuum bagging, so that the higher viscose epoxy that we embedded with nanosilica can flow inside and bond with Arenga Pinnata. All right, that's the conclusion that I made. Okay, so
Okay, thank
that's
you.
all from me. Thank you so much.
Thank you,
I'm
Dr.
sorry for
Khalid.